questions, let me know. If not, I'm gonna breeze through this pretty quick. Nothing new. These are all pretty basic. These give you a pretty good rundown of like what to kind of expect on the exam, but a little more distilled, right? Don't expect the exam to be like this easy, right? But this will be if you're just need a sandy check, run through these, it'll be fine. So without further ado, we've got three of them. First one's a dimensional analysis thing, like what you're reading here, and then the other two are like pipe flow, head loss stuff. So anyway, in 1940, fluid dynamicist G.I. Taylor determined from dimensional analysis that the radius r of a fireball created by a nuclear explosion is exclusively determined by the energy released E, initial gas density rho naught, and elapsed time since detonation T star. Note that 1 kiloton is 4 times 10 to 12 joules. Part A, find the single pi group that controls blast radius R. And in 1945, a 20 kiloton bomb was tested in New Mexico. On that day, air density was rho naught is 1.23, yada yada. A photo taken at T star, yada yada, shows fireball of radius 108 meters. Compute the value of the pi group from part A. So we're going to find that pi group in part A and then plug in the numbers for part B. It'll be really easy. And what do you think was going down in the New Mexico desert in 1945? What do you think that was? Yeah. Anyway, so for part A, let's get our we only have four parameters that we're working with, so let's get them down. Right, we've got some radius, which is a length. We've got some T star, which is a time. We have some density, and we have some energy. And energy is the only one I wouldn't know off the dome. I'd write this, the weird ones like energy and, ideal gas constant, stuff like that. Write those dimensions down. This one is just ml squared over t squared. I'm not going to break down the whole problem for you. This is a really basic one. But, three dimensions, pick three parameters, right? And those three we're going to pick, just for simplicity, we're going to pick R, T star, and rho naught. So we're going to solve for E. Right? And we did that, and I get like this one's kind of funky because we want to find the pi group that controls the blast radius, but we're picking R as one of our repeating variables, which kind of breaks an unwritten rule. It's fine, okay, as long as the stuff you pick is pi group, like what we set up top, right? So let's go pi 1 equals E times, let's go R to the A, T star to the B, rho naught to the C. And so this becomes what's our dimensions of E? ML squared over T squared times L to the A, T to the B. And so now set exponents to 0. And solve. So you'd have your m's 0 equals, in this case it's 1, nothing, plus c, right? C equals 1, blah, blah, blah. Repeat. Yada, yada. I'm not going to do the full thing. This is pretty basic. Just go back to look at your notes. This is not what will be tricky on the exam. Get the system of equations, plug in your calculator, slap in the RREF, reduce row echelon form. That'll get you your numbers for you. At any rate, you end up getting pi 1 equals, and like the form we ultimately find, we had R as one of our repeating variables. So we end up bringing that up top, and like that's the thing we're going to be like dividing our stuff by. So we end up getting R over times C star to the 2/5, and that's a 2. Sorry, it's a 2. So I do even see by the next ones on here, there would have been like a fair amount of legwork to actually do once for like solving for A and B, whatever. Go math it out. Again, your calculator can do it for you. And we put it into this form because we wanted the pi group that controls blast radius R. So like we kind of wanted R isolated on top. But like I said, whatever the numbers work out being, really, as long as you have a non-dimensional pi group, you're gonna be fine. I was telling some of the other recitations, like, we actually kind of prefer you not to simplify stuff super nicely because it makes, if you mess up, right, and you simplified the mistake you made into a completely foreign format, right, it's going to make it even harder for us to grade. So, whatever. Anyway, this is the pi group right here. All done. That's part A. All right, now part B, we're given rho naught was 1.23. T star was 0.015. R equals 108. And energy, it's a 20 kiloton bomb. So 20 times 4 times 10 to the 12 joules. So just plug everything in. Ooh, just plug in. Let's get pi 1 equals 108 over 20 times 4 times 10 to the 12 over 1.23 all to the 1/5 times 0.015 to the 2/5. If you plug that in, you get pi 1. It's about 1. Depending on how you round, 0.99, yada, yada, 1.01, blah, 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 whatever. Same diff. Yeah, literally, that's easy. Easy, easy. Like I said, I expect something a little trickier than this on the exam. This is kind of trivial to do, right? One pi group, but gives you a nice little flavor of what to expect. If you totally forgot how to do this, this one's kind of nice too, because yeah, it would make you do quite a bit of legwork with A's and B's and C's and stuff, but the concept is there. And I was also saying, don't forget how to non-dimensionalize an equation. I can't guarantee it will or will not be on the exam. Some semesters we throw non-dimensionalizing equation on there. Sometimes we don't. I don't know. You've got like 3 sheets of notes though. Might as well throw it on there, right? Put an example on there. Who cares? You got plenty of room. Yeah, that's all I gotta say about that though. Any questions? No. Just remember your rules for picking your repeating parameters, right? They can't form a non-dimensional group within themselves, right? They have to cover all the primary dimensions, all that good stuff. Let's go back to look at your notes. Should be easy. Should be pretty nice. Okay. Moving on. Question 2 is similarly pretty chill. Question 2 and 3 are very similar. So anyway, here's question 2. We have water being pumped at 0.003 cubic meters per second in the top of a truck. This is a truck. It's supposed to be a truck. It's a tank. Let's call it a tank, whatever. I'm no artist. They're a 40 millimeter diameter hose. If the length from C to A is 10 meters and the pipe is smooth, determine power output of the pump. All right, so this one's pretty easy. You're going to be looking for some. Okay, so here's what I'm doing on these. I'm like, all right, do I have some Q value, some volume flow rate? And boy, do I. So sweet, got that. And do I have a diameter? Yeah. So this is just going to be a plug and chug, make some money type problem. The only thing we have to worry about is we want the power output of the pump, not just the pump head. So a good equation to have is W dot P equals rho G Q times HP. Right. I would always forget that when I took this class. I would always have it written down at the top of my paper. That's really the only tricky part about this whole thing. And so now we can just start plugging stuff in. So we're going to take, it's water, so we're going to take density, it's just 1,000, whatever. Dynamic viscosity, that's a pretty standard value right here. Pascal seconds. So we got Q equals 0.003. We have diameter is what? It's 0.04. L is 10. Then we can also make some other little assumptions. So let's call ZC 0, because we're going to have to be using some Bernoulli's at some point, right? So let's call ZC equals 0. And so ZA is 2 plus 3 is 5. ZA is 5 meters. And we can also say PA equals PC equals 0. They're both open to air, right? It's not immediately obvious. For the sake of this problem, and like they'd give this to you on an exam, for the sake of this problem, we're assuming the hose is just like resting on the side of the tank. It's not like attached and pressurized or anything. It's just like sitting there. So both of them are open to air. We can also say VC equals 0 because it's a big reservoir. So anyway, it's pretty much all we really need. Because you're if you have any foresight with these, right? If you've done enough of these, you're going to be taking like a Bernoulli's from point C to point A because you want to know the power of the pump. So you have to pick 2 points where the pump goes between. So if you went from C to B, right, the pump is technically like not right there, right? It's like right. If you take the limit as it approaches like point B, the pump is like not included in it. Same thing from B to A. So go worry about that. And there's just not enough info at point B to really plug and chug. So anyway, step 1, let's find a velocity so we can find a Reynolds number, so we can find a friction factor, so we can find a head loss, so we can find a pump head, right? So we know V equals Q over A, which is pi over 4 D squared. Plug that in. And V is 2.3873 meters per second. And now find Reynolds number. It's our classic rho VD over mu. You know everything. And yeah, like on an exam, if we're just talking about water and we don't give you the viscosity or the density of water, just use the standard values. Like in this case, we're using 1,000 and 1.003 times 10 to the -3. It'll get you there. So plug those in. The Reynolds number equals 95,206, which is turbulent. So alpha equals 1. And does anybody remember the laminar limit, right? It's like 2,300, right, for a pipe flow. Don't forget that number. Since you don't do too much with it on homework and stuff, he might throw it on the exam just so you remember it. And either way, laminar stuff is pretty easy to work with. The equations are nice. So anyway, turbulent. Right, use Moody/Tolbert for F. Doesn't matter. Recall that Tolbert is 1 over root F. And again, I'm not going to lay this whole thing out. It's just math. But if you were to go and use Tolbert, right, this epsilon over D term would go away because like you could very well throw minor losses on here, right? You'd have like a sudden expansion into the truck, and then loss from getting sucked into pipe C, right? at point C. But we're just assuming there's no minor losses. And again, on the exam, we'll tell you if you need to include anything. So don't worry. So in this case, HF equals HF major equals F L over D V squared over 2G. And again, plug in. You know everything here. There's nothing here left to solve for. Just plug everything in. HF is 1.30715. And try and carry a few decimals, a few more than usual in the middle of these problems. And then lop them off at the end if you want to. We don't want any like cascading error to follow through the whole problem. Because like, I'm sure working on the homework with your buddies, like you saw, if you have a slightly different F value, you can really throw your answer off. So keep a few decimal places. All right, cool. So we're pretty much done solving for stuff now. So let's do Bernoulli's. From C to A. And so we're going to have and yes, please on the exam, please write out the full thing at least once. Okay. Show me that you know what you're looking at. So again, let's cancel some stuff out. There's no turbine. We don't care about that. We're saying point C is at 0. We said the pressures are both at atmosphere, so those can go away. And the velocity at C is 0 because it's a big tank. So literally, we're just left with HP equals, and alpha is 1, like we said. So it's just VA squared over 2G plus ZA plus HF. And so plug everything in. We know the velocity A is just the velocity in the pipe, right? Right as it's coming out of the thing. So HP equals 3873 squared plus 5 plus 1.30715. Right? So we get HP is 6.5976 meters. And now just plug in. So we get WP is rho G Q times HP. Plug in. It should be 194.167 watts or joules per second if you prefer. Same diff. Cool. Yeah, this is a pretty standard one. Plug, chug, find some stuff, keep plugging, do a little more chugging. All right. Nothing wild. Any questions? Sweet. Yeah, again, I mean, there's another one right after this that's very similar. And really the only way we can make these any tougher is just throwing on a bunch of like minor loss coefficients. But again, you just tap those onto the HF term. I mean, it's not hard. This is why I say exam 3 is never all that tough, because we're not going to make you do any super brutal iteration because you just don't have time to. You've got an hour and 15 to do 3 questions. And there's just a lot of little calculations you got to do. So we're not going to make you do anything super brutal. Oh, and I said 3 questions. Who knows? Might be 3 questions. It's not like they tell me, right? They don't tell me anything. I'm a loudmouth. You guys have met me. You think they let me in on any secrets? No. I just know from experience. So, anyway, yeah. Last one, like I said, very similar vibe. So there's just one other little tweak to it. That's easy. So we've got oil with density of 900 kilograms per cubic meter and kinematic viscosity of 0.00001 square meters per second, flows at 0.2 cubic meters per second through 500 meters of 200 millimeter diameter cast iron pipe. Determine the head loss and the pressure drop. The pipe slopes down at 10 degrees in flow direction. So a little notation thing. Let's draw it like this, right? Where we've got a 0.1 right there. We're sloping down to a 0.2. And this is the 10 degrees we're talking about. So when we go and do our Bernoulli's equation, inevitably from 0.1 to 0.2, right, I'm going to have 0.1 be z1 equal to 0, and then z2 just have it negative. You could just as easily do the other way around. It doesn't matter. Anyway, so the only other thing we really need to know with this problem is so it's a cast iron pipe, so we have some surface roughness. And they don't give it to you in here. They don't even give it to you in the problem statement. You just have to like assume it. On an exam, we will give you a table of this stuff, so don't worry. Right? We'll be very explicit. And if we forget to give it to you, raise your hand. Come tell me. I'll write it on the board, or I'll tell you. Well, you don't really need it. So either way, just raise your hand and ask me. At any rate, epsilon is 0.26 millimeters. Right. Well, so now we know everything else. So let's go again. We want to find a velocity, right? We've got a volume flow rate and we've got a diameter. So let's get our velocity straight up. Right. And I'm not rewriting, Q, what Q is. Q is 0.2. Diameter is also 0.2. So we get V equals 6.4 meters per second. Again, let's get a Reynolds number. And in this case, we have to use the VD over nu form because we don't know the dynamic viscosity. It's not just water, it's oil. So we have to use VD divided by nu. And doing so, you get RE. It's about 128,000, which is turbulent, very turbulent in this case. So alpha just equals 1 again. So now, again, use Moody or Colebrook for F. Or whatever other crazy equation you want for F. At any rate, F should be about 0.0225. Again, like I always say, picking 0.02 is a good starting point if you ever just need to get out of a jam. Won't guarantee your answer will be right, but you'll be in the right ballpark. So keep going. So let's find our head loss. And also remember epsilon over d in this. Right. Some people like just lopping that term off arbitrarily, even though there's definitely like they just assume it's smooth for some reason. No. Like if we give you like a type of pipe, right, it's for a reason. Anyway, so we've got our F. And so again, HF is just equal to HF major. We're ignoring any minor losses, right? And I mean, we're assuming we're just taking like a snapshot of the inside of this super long, like, oil pipeline. So there's no twists and turns. There's no entrances, outlets. It's just one point, another point. And we're going down a 10-degree hill. So we got HF equals F L over D B squared over 2G. Again, we know everything. We found our velocity in the first step. So in this case, part A is just, we're done. Just put everything in. Should be about 117 meters. However you went around, be my guest. I don't really care. So there's part A done. Right? And so now for the pressure drop, let's use Bernoulli's from 1 to 2. So we're going to have P1 G plus. And again, there's no turbine, there's no pump. The velocities are the same, so when you go and subtract those over, they cancel each other out. Like I said to start off, I'm gonna call Z1 0. You could call Z1 the height or Z2 the negative height. I'm calling Z2 the negative height, so let's cancel that out. So we're left with P1 over rho G equals P2 over rho G plus Z2 plus HF, right? So now subtract the P2 over, multiply the rho G. So we have delta P equals rho G times Z2 plus HF. And what's Z2? Z2 is, we're going downward, so it's negative length of the pipe sine 10 degrees. So plugged in, we have delta P equals 900, 9.81 times negative, this is negative 87. So we have negative 87 plus 117. So we get delta P should be about 265 kPa. And voila, we are done. Right? Yep, 265. Cool. Cool. Yeah, again, pretty easy. This is, at the very least, if you just need to go and get the concepts down, these three are a pretty good place to start. They're a little basic, but they'll get you where you need to go. Go and go and do one with a minor loss coefficient stuff on there, right? Don't forget how to do that stuff. But it'll be cool. If you're good at these, you'll do fine on the exam. Trying to think anything else. No, not really. I mean, that's about it. Get your dimensional analysis and get your pipe flow stuff, and you'll all be golden. So good luck with that. Any questions? No? Sweet. Let's end a little early. All right. Anybody on the online section, as always, shoot me an email if you got a question. Have a good one.